So, today's topic is about data acquisition. So, you will be building a simple data sampler today. And basically what it's made of, let's open this one here. Come on. I can get that one or two be a different screen. There we go. Okay, it shows more or less the whole thing. But anyway, so the data acquisition, for example, if you want to record a voice. So what a voice recorder is made of is there's some sort of the amplifier, then there's sample and hold, or some analog filtering, and then sample and hold, and then A to D conversion. So that's the basic signal route. So basically we start with the small analog signal, say tens of millivolts, maybe hundreds of millivolts. So in principle, these dynamic microphones are designed so that in normal usage, the signal is between plus and minus 200 millivolts. That's the design thing, but that's small compared to A to D converter, the conversion range. So that range is usually volts. So you need to have some amplification for the signal before you get it to the A to D converter. But also you need some cleaning up. So there's usually some spurious noise on your signal, and basically you need to clean it before getting further. Then usually the sample and hold is part of A to D conversion. But in some A to D converters, you still need to have a separate one. Usually the successive approximation registry type of A to D converters are really sensitive for the changes during the conversion. So that's why there is a sample and hold. But on the other hand, for example, sigma delta A to D converter basically integrates this time, so it means that it's not that sensitive for the changes. But anyways, the principle is that you stop the sample at a certain sampling rate, and then you convert the signal to digital. And digital means that you have also quantized the values. So on the beginning you have analog signal in continuous time and continuous value. At middle, the sampled signal means actually discrete time. So digital signal processing actually starts here. It considers the discrete time signals. And at the end we have the digital signal, which is means discrete time and quantized value. Okay. And there's a cat. So a couple of things about the sampled signal. In principle, discrete time, but also continuous value. It's easier to handle actually. So a couple of important things when you do any sampling of signals, try to use a constant sampling rate. Otherwise, it will be a scrutinizing effort to try to analyze the signal. So arbitrarily sampled signals are just single samples in time, and you cannot make, for example, any spectrum analysis based on that one. You need to have continuous, constant sampling rate signal samples. So yeah, sampling rate, constant sampling rate, and then basically there's another term, sample time, implicit sampling interval, which is just 1 over the fs. Then you probably have heard of Shannon's theorem. It basically states that you must take at least 2 samples per original signal period in order to digitize the sinusoid signal. If you have too long sampling interval, then that leads to aliasing, which is shown here. The blue, the signal here would be the real one, and then basically if you sample it on these red dots, you are actually sampling a sinusoid, but it does not represent the real signal anymore. So in this case, you will either have to filter these high frequency signals before they enter the A to D converter, sampling before you sample them, or have higher sampling rate. Okay, then just a reminder, okay, the digital signal compared to the previous sampled signal, the difference is only that we are quantizing the signal, and then there's signal to quantizing noise ratio defined like that, which basically gives you the dynamic range of any sampled signal compared to how many bits you have. So high quality audio signal, usually you are using at least 16 bits. It basically comes from here. 16 times that is enough of decibels to have a nice the audio quality signal. For example, the human ear, you can still detect to 20 kilohertz. I'm not. The hearing, well, the high frequencies deteriorate by age. That's a common fact. So, but anyways, you still can hear 20 kilohertz. To keep your hearing, you should never listen loud music. Or play in heavy metal band that I did. But anyways, okay, so in order to sample those 20 kilohertz signals, you need at least 40 kilohertz sampling rate for good audio recording, and that's actually where the CD quality postcode modulated signal has the 44.1 standard sampling rate. It's higher than that because you need also some marginal for the analog filter. Okay, meaning, just draw it quickly. Meaning that if you want to sample up to 20 kilohertz and you have analog filters, basically you need to have the anti-aliasing filter, and it has the edge. You need to filter those spurious high frequency things out before that 22.05 kilohertz, which is the Nyquist frequency for that one. Okay, so there's a reason for everything. Okay, and listening music requires anomaly sound pressure levels in range of pin drop to hurting your ears. So 20 to 100 decibels. That's actually something the classical music easily gets the, this is piano pianissimo and this is forte something. Yeah. So it means that you need to have at least signal to quantization noise ratio of 80 dB, which is more than 13 bits And basically that's why CD quality PCM signal has 16 bits resolution. And well, professional audio has 24 bits. And basically because of some nasty features on the Sigma Delta HUDs, they require that 24 bits in order to have a good audio quality. But the Sigma Delta, the type of HUD converter is quite nice actually for that purpose. The Sigma Delta, the HUD converter basically, it has, since it's also integrating, it means it has this first order, the decimator on it. So basically the signal to noise ratio of that goes like that one. So basically in order to have the nice at least 8 bits at the high frequencies, you need to have that 24 bits for high quality audio. Okay, there's also reason for that one, why we need so many bits on the HUD converters. Okay, so, but anyways, that PCM signal 16-bit resolution, just fine. Yeah, signal to noise ratio, we don't need that one today. We are not interested about measuring signal to noise ratio. We are interested to have some signal and measure it with this nice programmable system on the chip circuit. Okay. Let's take it the exercise. So today basically we start by taking out the this servo motor. You will be needing the prototyping port, analog sensor, and potentiometer. We actually have, the potentiometer is nice since then you can play around with this, where do we need? There, here. Then you can play around with the device. So we have this nice sliding potentiometers here. So first thing is, okay, there's plus and there's minus terminal here, and on the other terminal, the terminal 3 is probably, or maybe, let's see. This is very mechanical potentiometer. I think we used hook this signal, a plus and minus between 1 and 2, and then the terminal 3 is the output, or is it? No. No. Okay. You connect 1 and 3 between ground and the operating voltage, and then basically terminal 2 gives you the signal. But this is actually quite nice. You can easily test your system if your HUD converter is working. Because basically when you are working then with this that one, analog sensor, analog temperature sensor. We have somewhat in constant temperature here. The room temperature is 23 degrees or something like that. And your fingertips are something like 30 degrees, not 36. Otherwise you will have fever and you shouldn't be here. Okay, so your fingertips are usually colder than the rest of the body. So So it's about 30, 31 degrees. It's only a few degrees difference from you to your fingertips and this one. So you wouldn't get big changes. So it's hard to test your system just with the real sensor. So that's why you'll be using, on the beginning you would be using the slider to get some value out of the A to D conversion. Okay, so you'll be needing those, one of each. Okay. What then? So you would be basically doing something like that. Wow. A to D converter. On software side, you would be doing downsampling. So you collect information from a fast running A to D converter and basically do decimation, meaning the simplest way, what I recommend for you is just to calculate the average value for certain time. Sum every single measurement that A to D converter has done, sum them up, and at certain rates you will calculate the average and start over the summing. And the average is something that you will be sending. Wow. But for beginning, we are starting from an example. That's nice of me. Since basically you can first take a pre-tested design that actually reads the values on A to D converter and sends those values to computer via this USB UART bridge. So on Monday you already experienced with this UART thingy getting some values from the board, and also pressing the key sends the value. So it's nothing more than that, but now you just basically start from this example, connect a potentiometer for your signal source, put it on the port 0.0 pin, and then the system reads an ADC value, transmits your UART. Your first task is to make sure that you can read the value from the potentiometer. Okay, next step, modify. Instead of that potentiometer, well, actually, that will be the last thing to do. This analog temperature sensor is cheap, but it has a really annoying feature. These burn extremely easily. So use them only when you are sure that your rest of that program is already working. Okay, so use the potentiometer instead. This withstands something like, I'd guess, 10 watts power consumption or something like that, because it's big and bulky. The extremely dangerous for these circuits, actually this real sensor, is to reverse the polarity. And old school electronics teachers know that when you have this kind of package, the pin out is given from the bottom side, not the top side as for other integrated circuit packages. Since this is on old transistor type of package. So when you are looking at the bottom side, then you are quite sure that, okay, these are the pins. But if you are used to look these data sheets from the top side, you will reverse the polarity and you will burn these. Okay, now you have been warned. and now if you burn one, we can charge you. No, we are not going to charge you. We just make big funny jokes on you. Okay, okay, so basically this A to D converter, you will modify it free running at any range between 1,000 and 10,000 samples per second. Actually, the A to D converters on this board are pretty fast by default. They are designed for, say, continuous sampling, and with, say, with this 1,000 samples per second, that's typically how you sample, say, some biometric signal. 10,000 samples per second, you can already do some, say, audio recording of human speech, some that kind of things, or some sound analysis purpose. Anyway, as long as you make the A to D converter, could you go fast enough, the exact sampling rate is not critical. Since what you will be doing is there. Okay, so let's see. Twice 2 samples per second, so 0.5 seconds, 1 second, and your real sampling rate is whatever. You will basically calculate the sum of values and divided the number of samples. And you do basically the same thing for the next half second and so on. Sum divided by n. But of course, both sum and the number of samples that fit into that period will be different. Sum, of course, because it depends on the value of the A to D converter reads, but also this by default is have a jitter. The sampling interval, the data that you are sending is just 2 samples per second, meaning half second summing intervals, and basically you can have plus minus 1 these fast samples in there by default, and then there's also some other jitter due to the, well, if you are running a complex system with interrupts, several interrupts, you never know which interrupt is basically slowing down the A to D conversion process or calculating this sum. This also takes some time. Okay, but anyway, the system calculates the time average data with new downsample rate of 2 samples per second. Okay, and then there's downsampling clock has to be interrupt based. Yeah, you know how to do interrupts now. It was yesterday. I can also do a review of the interrupt thingy. And then you need a mechanism to calculate the running sum of the A to D values without side effect. Here you have an excellent chance to have a side effect of, meaning that the value you are using is changing during your calculation. Okay. So practically, if I were you, I would actually calculate this sum and also keep track on how many samples there are on the sum on A to D converter interrupt service routine. So make the A to D converter to interrupt, give interrupt request, and then on the interrupt service routine you go and read the current A to D conversion value and update that one and clear the interrupt. Right. And then you can use, say, non-volatile static variables, or actually what you could do is just you have global variables to save the values. So this has to be basically So there are so many ways that you can actually do this one. So I will let you to think of your method. It's probably better. But anyway, so you need to calculate the running sum and keep track on how many samples there are on the sum. And in half-second rate, you will go and fix these values so that they do not change. There are different ways of doing it. You either stop the A to D converter so that it doesn't interrupt anymore, or you take these values and make copies of them. Okay, so at this rate you will take the basically sum x equals sum, the running sum, and sum nx equals the current n, and after that you actually can start over with the new values. You can start summing up again and calculating new values. Okay, this is one way. And after you have done that one, you can calculate the average. If you try to do this sum divided by n, or sum 1. There's no guarantee that there will be interrupt in between of this operation. Especially since you are summing up something like 2 byte long, so basically you are summing 32-bit integers. Well, you still can have a trouble on that one, since it could be that either one of those changes in between because of this rapidly interrupting A to D converter. To make sure that this doesn't happen, you put those on intermediate values, or actually disable interrupts and enable interrupts. Even more safe way to do it. Okay. And yeah, then you won't have the classical side effect. Okay. Convert the average A to D value to corresponding temperature in Celsius degrees. All right, so these classical LM35 type the temperature sensor actually gives 10 millivolt signal for centigrade. So we are expecting something like 230 millivolts in this temperature, or when you put your fingertip on it and warm it, then it would be 300 millivolts around. So those are the signal ranges. But you need to do the calculation so that it basically is a temperature sensor. Haha. And then transmits at downsampled rate the A to D value and corresponding temperature in Celsius. Wow, this is, I would say this is extra. If you want to, this is easy JSON data format. But I would be really happy to see the just 27C on the terminal window at rate of 2 samples per second. JSON is extra. That would be actually, then you would have a system that you can, for example, have a software on your computer that reads the JSON data and or just stores the JSON data. Since that's the kind of universal way of saving some, say, simple data. Okay, so JSON is extra, but you need to get the centigrades right. Exercise report. Yep, and then you return it using this return link, following the instructions. Wow, that's a lot. Any questions on this? Okay. Let's start the SOC creator. I will show you a couple of things there. There we go. So on the start, there's this one, at the middle, there's selection of kits, and under that there's the selection for these. You can actually start by opening this one, saving it as a template, and then continue on that one. But on the other hand, I don't mind if you go and just start working on that one. Although if you want to keep that one in good place, let's see, I'll try to create. Let's see, yes, you can actually do it from here. Select project template, code example. And there was the which was the okay, ADC and what here. Let me check if that is exactly the same. 1952778. Yeah, it's this one. Okay, we start with that one, and now you can actually change the names again. PSOC. Design. Oh, 3. Oh boy, it has again this. PSOC design 03 and project name PSOC design 03. Oh, it also opens the data sheet. Yeah, it's actually a good idea to go and read this data sheet before you go, but well, I'm lazy. So don't do as I do, but do as I tell you. So read the instructions first. But anyways, this is quite simple and well documented example. That's an excellent example how you should comment your code and design. You can add this kind of text boxes on your design. So we have on this design we have A to D converter and WART. That basically is most useful transmit. Okay, that's fine. And let me do the generate application. Clean up. And then main. Oh, wow. Look at this one. It's mostly documentation, not too much the code. This is something to actually take a good look at and do the same. Okay, so we have a couple of variables on the beginning. There's the transmit buffer. Okay, it starts the delta sigma and it starts the WART component. Initializes the variables. Then it starts the conversion. I think this will start the conversion so that it's continuously running. And basically it even uses the switch. Oh wow, this is fancy. So basically it reads whatever the user wants. There's a continuous sampling, then the single samples, X probably ends the continuous sampling, or E is the end. And then basically just goes and check if there is something to convert, or if there is a conversion ready. Then basically it reads the delta sigma. Oh wow, it also even has the interesting. So there is a function that returns the millivolts. How many millivolts was the ADC result? You can use that one. That probably would be a nice way to go, since you know that your signal is some hundred of millivolts. It makes much easier to calculate the real temperature that way. And then basically, what does it do? Yeah, just makes the string using printf to transmit buffer sample %LU, so it's long unsigned, I think, in millivolts, and this is carriage return line feed. Yeah, and then the value, and sends it to the transmit buffer. And then there's some send single byte false. Okay, yeah, whatever that is. But anyways, it's a very quite simple code example, but it has lots of things going on there. So yeah, so variables, starting the components, initializing the variables, then it starts the A to D conversion. Okay, and you see the rest. So basically what you could do is to start with this the example, try to get the millivolts out. So let's see, if I'm not totally wrong, it was yeah, I think it works like I said. Between 1 and 3 there is a kind of charcoaly glide there, and the other one is silvery, so it must be like that. Oops. The slide. So it looks like this. 1, 3, and 2 is the sliding part. So you can connect this one to VCC, this one is ground, and this one is connected to port 0.0. Then you should start reading some values. But read this datasheet first. Okay, any questions? Other than, can we start? Yes, you can start. Yes, you can start working.